All right. So part 2, 14.7, spherical coordinates, triple integrals. All right, so reminder quickly about spherical coordinates. Just so we get back in our heads how they work. X is rho sine phi cosine theta. Y equals rho sine phi sine theta. Z equals rho cosine theta. Sorry, not cosine theta, cosine phi. And for spherical coordinates, rho is our radius, is greater than or equal to 0. Theta, same angle as in cylindrical or polar coordinates. So cylindrical, polar, we're using the same angle there for theta. And phi is measured from the positive z-axis. And phi varies, phi goes from 0 less than or equal to phi less than or equal to pi. We're going from straight up to straight down. So what we're going to do is we're going to develop this idea of a triple integral in spherical coordinates, just like we did for cylindrical coordinates, just like we did for polar coordinates in the plane. So we want to divide our solid region into little chunks of a sphere. So that's our idea here. So draw a picture, and we'll label all of our pieces to come up with a representation of our volume elements in spherical coordinates. So we're going to have a little, up here, up above the XY plane, we have a little piece of a sphere. So we're cutting out little spherical pieces. A little chunk of a sphere there. Oops. Cutting it out. So we're going to find representations for the lengths of the sides of this little piece. I know it's not a beautiful drawing, but we get the idea. We're cutting a little piece out of a sphere. We're going to come up with representations for the lengths of the sides of this. We're going to say this is approximately a rectangular block if we make the sides small enough. So what I'm going to do is I'm going to draw some, I'll do this in a different, do dotted lines here. And we're going to project this down onto the XY plane as well, and we're going to look at this projection down on the XY plane so that we can think of this as the shadow of this little block, the edge of the shadow of the little block in the XY plane. Well, in the XY plane, this little piece, this little change is delta theta sub I, and the length of this little arc from polar coordinates is r sub I delta theta sub I. And I'm going to substitute in for r sub I in, if I convert our radius in polar coordinates to cylindrical coordinates, this gives me rho sub I sine phi sub I delta theta sub I. This little angle here is delta phi sub I. So our little angle in here is delta phi sub I. The length of this side of the block is delta rho sub I. Put a little arrow here. So that distance is delta rho sub I. So this side of the block is the same as this little piece. So this is rho sub I sine phi sub I delta theta sub I. And this little arc here is going to be rho sub I delta phi sub I. So this is just a little piece of a circular arc moving in the phi direction from the z-axis. So that little piece is rho sub I delta phi sub I. So we have all the sides. We have three sides of our little spherical, approximately rectangular block. So delta v sub I, the volume of this little block, what we end up with when we put all of these pieces together, delta v sub I, is approximately rho sub I squared sine phi sub I delta rho sub I delta theta delta phi sub I delta theta sub I. So we get the sine phi sub I from this side, we get a rho sub I from this side and from this side, and then we have all of our deltas there. And we're going to do just like we did previously. We're going to sum over all of these little blocks in our region to get the volume of our solid region. And we're going to take the limit as the volume delta, all these little delta rho, delta phi, and delta theta get smaller and smaller. And again, we're talking about making the longest diagonal shorter and shorter and shorter. And to be a little more precise, we would use our average rho and our average radius here, just like we did in polar coordinates. But what I'm looking for is to get the idea here of how we put together this triple integral. So this is our volume element: rho sub I squared sine phi sub I delta rho sub I delta phi sub I delta theta sub I. So we take the limit as delta v sub I approaches 0, and this gives us our triple integral in spherical coordinates. So this is our volume element. So our triple integral the integral over some solid region, triple integral over some solid region Q of f of x, y, z dv is going to be the integral from theta 1 to theta 2, the integral from phi 1 to phi 2, the integral from rho 1 to rho 2 of some function, and I'm using capital F because we're going to convert our function to spherical coordinates, rho phi theta, and then our volume element always in spherical coordinates, rho squared sine phi d rho d phi d theta. This is always our volume element in spherical coordinates. So all of those pieces have to be in our integral when we evaluate triple integrals in spherical coordinates. So just like r dr d theta was in polar coordinates, and r dz dr d theta is in, we have all of those pieces in cylindrical coordinates. We have to have all these pieces for our volume element for spherical coordinates. We can talk about variable limits. Here we have constant limits of integration, variable limits of integration, the exact same thing that we've talked about with all of our triple integrals. And we can talk about different orders of integration. We could have any permutation of these three to give different orders of integration, just like we did previously. Most common to have this order of integration: d rho, d phi, d theta. And usually when you're setting up a triple integral, for what we'll do, usually what we'll do is we'll set them up in this situation. And when we set up a triple integral in spherical coordinates, our limits of integration are nice, usually nice, easy to work with. Often they're constant. We might have a variable limit on our rho, but in general, when we can set up an integral, triple integral in spherical coordinates, our limits are going to be pretty nice, pretty easy to work with. Now we always end up with this sine phi in our integral, so we end up with trig integrals that we have to evaluate. But often when we can set up our integrals in spherical coordinates, it's much, much easier than setting them up in rectangular or cylindrical. So questions on our setup here. So the most common mistake in spherical coordinates is forgetting that this entire thing is our dv, this rho squared sine phi, d rho d phi d theta. You have to have that entire thing. Just like in polar coordinates, the most common mistake is to forget that r in there, the r dr d theta. All right, so I want to do a few examples using setting up and evaluating triple integrals in spherical coordinates. So let's look at an easy one first. We want, so here's our triple integral, 0 to 2 pi, 0 to pi, 2 to 5, There's our triple integral. We want to sketch the region and evaluate the triple integral. So we look at our limits of integration to sketch our region. From the limits, we know that 0 less than or equal to theta, less than or equal to 2 pi. 0 less than or equal to phi, less than or equal to pi, and 2 less than or equal to rho, less than or equal to 5. So before we start sketching, anybody visualize now what are we talking about here? No, nobody sees it yet?
Sphere with a hole in the middle.
What is it?
Sphere with a hole in the middle.
A sphere with a hole in the middle. Our radius is varying from 2 to 5. Our theta is varying from 0 to 2 pi, so we're talking about all the way around the z-axis. Phi is varying from 0 to pi, so we're going from vertical to horizontal. And we have 2 constant radii between 2 and 5. So we have a sphere with a hole in the middle. So if I draw a sketch here, I'm just going to draw it in the first octant. Well, here is a sphere with radius 5. And here is a sphere with radius 2. So we're evaluating this integral all the way around here, and it would go down into the lower octants here. We're evaluating from rho equals 2 to rho equals 5. So what we're looking for, rho squared sine phi d rho d phi d theta, is dv. So what we have is the triple integral over q of dv. What's the triple integral over a region of just dv? That's the volume. We're looking for the volume of this spherical shell. So we could evaluate this integral, or we could be smart and say, how do we find the volume of a spherical shell? Volume of the big sphere minus the volume of the small sphere. So this is going to be 4/3 pi times 5 cubed minus 4/3 pi times 2 cubed. And we end up with, when we do this, we get 156 pi. So this is just the volume of that spherical shell. We could evaluate this integral, and you should come up with the same answer. Questions there? So this is one where we want to use geometry. All right, let's look at the problem that we did yesterday with the cone and the sphere, and set that one up in spherical coordinates rather than cylindrical coordinates. And we can compare and contrast. All right. So we wanted the volume. What we found was the volume under x squared plus y squared plus z squared equals 4. And we were above z squared equals x squared plus y squared. So we had just a quick sketch here just to remind us what we're talking about. We have this sphere, x squared plus y squared plus z squared equals 4. That's a sphere, radius 2. So there it is in the first octant. And then we had a cone. That intersected this sphere like so. So we're trying to find the volume inside the cone, above the cone and under the sphere. So the volume inside. So what we said yesterday was we're finding the volume of our ice cream inside of our ice cream cone. So we want to set this up in spherical coordinates rather than in cylindrical coordinates. Yesterday we set it up in cylindrical coordinates. Setting it up in spherical coordinates is way easier. On the sides of the cone, we have z equals x or z equals y. What is do we remember, because we had this question on a test once, quiz once, the equation of a cone in spherical coordinates? If z equals x or z equals y, what's constant there? Phi is constant. The equation of a cone centered on the z-axis is always phi equals a constant. So if z equals x or z equals y, what's our constant? Slope of 1. What angle gives us a slope of 1? 45 degrees. So phi equals pi over 4. That's the equation of the cone. We don't have to have any x squares and y squares, anything in there. That's our equation. So phi is going to vary inside the cone from 0 at the z-axis to pi over 4 on the cone. So we get 0 less than or equal to phi less than or equal to pi over 4. Nice, easy limits of integration. We're integrating for the entire sphere. So theta is going to vary from what to what? 0 less than or equal to theta less than or equal to 2 pi. We have a whole circle. And the radius of this sphere is 2. So it intersects up here on the z-axis at z equals 2. So 0 less than or equal to rho less than or equal to 2. Our radius is varying from 0 to 2. So our volume in spherical coordinates is going to be the integral from 0 to 2 pi, the integral from 0 to pi over 4, the integral from 0 to 2 of rho squared sine phi d rho d phi d theta. Much easier to set up, a little easier to evaluate here. All of our limits are constant, and we would end up with the same answer that we got yesterday. Much easier to set up because our situation here has spherical symmetry. It has cylindrical symmetry also. We ended up projecting this intersection yesterday down onto the xy plane, and that gave us our region that we could represent in polar coordinates easily. But this is a much nicer setup. Questions on the setup there? All right, let me take a look at what else I want to do here. Okay. Let's look at a mass integral. We want to find the mass of a solid. So let's find the mass of x squared plus y squared plus z squared equals a squared. So we have a sphere, radius a, and its density is proportional to the distance from the z-axis. So the density of any point in the sphere is proportional to its distance from the z-axis. So first thing we need to do is come up with an expression, write a function for the density. So we're going to say that rho is proportional, so we have some constant of proportionality. What's the distance of a point from the z-axis? I'll get us started. Square root. X squared plus y squared. So we could think of the Pythagorean theorem. We can think of the Pythagorean theorem to come up with this. But the distance from any point from the z-axis is x squared plus y squared. Square root of x squared plus y squared. So that's our density function. We're talking about a sphere here, so that suggests that we use spherical coordinates. So we need to express this in terms of spherical coordinates. So we get rho equals k times the square root of rho squared sine squared phi cosine squared theta plus rho squared, this is looking intimidating now, sine squared phi sine squared theta And we're taking the square root of that whole thing. So looking at this radical, does anybody see anything nice happening here? We have a cosine squared and a sine squared. So we can factor out this rho squared, sine squared phi. And we get times cosine squared theta, sine squared theta. That just gives us 1. So we're just looking at the square root of rho squared, sine squared phi. So this simplifies to a rho sine phi. So this look bad, not too bad now. So on our sphere, for our mass, here's our density. On the sphere, we're going to have 0 less than or equal to phi, less than or equal to pi, 0 less than or equal to theta, less than or equal to 2 pi for our sphere, and our radius is a, so 0 less than or equal to rho less than or equal to a. So we can set up our triple integral. Our volume is going to be k. This is just a constant. The integral from 0 to pi over 2. 0 to pi. Do I want to do it that way? Doesn't matter which order we do it in for this one. 0 to pi, 0 to 2 pi, 0 to, our radius is 0 to a, and we get rho to the third sine squared phi d rho, and for this one we did d theta d phi. The rho integral, very easy. We just have rho to the third. For sine squared, we would use sine squared, our identity that comes up a lot in spherical coordinates for sine squared and cosine squared, 1 minus cosine 2 theta over 2. And this is not, this turns out to be a very easy integral to evaluate. We just have rho to the third, sine squared. We just have this integral for our sine squared, and our limits on theta and phi are constant. And when we evaluate this out, if we were to evaluate this out, I'm not going to go through the evaluation, we get that the mass is 1/4 k pi squared a to the 4th. And just, whenever we set these up, I think about trying to set this up in rectangular coordinates, to set up this triple integral in rectangular coordinates and evaluate it, or even cylindrical coordinates. This wouldn't be horrible in cylindrical coordinates, but in spherical coordinates we get this nice straightforward integral. Questions on our setup there? So because we had this nice spherical symmetry, we had a sphere that suggests spherical coordinates, and this simplified nicely in spherical coordinates as well. All right, let's look at one more example. We want to find I sub x, the moment of inertia about the x-axis of the solid bounded by hemisphere rho equals cosine phi, pi over 4 less than or equal to phi less than or equal to pi over 2. And the cone phi equals pi over 4. So what we're talking about here is just a quick sketch. We have a cone like so, and rho equals cosine phi is going to be, put this in here, there's our cone. Rho equals cosine phi is a sphere radius 1. Do that in red. That's tangent to the origin. So let me extend this up a little bit. Black. So we're talking about this, the cone is going to intersect the sphere here. Let me erase these things and I'll make it a little nicer. So the cone is going to intersect the sphere in a nice circle here. So what we're looking for is the moment of inertia of the solid bounded by the hemisphere and the cone. So we're looking for the moment of inertia of the solid that's outside the cone but inside the sphere. So our moment of inertia about the, did I say I sub x? Let's make this I sub z, so we can use what we did in the last time. I sub z, the moment of inertia about the z-axis, we're weighting the distance of the point from the z-axis. So from our last example, we need the distance from the z-axis squared. So our distance from the z-axis we found in the last one was rho sine phi. Yes. And our density is going to be K. Just some constant. So we're going to we'll just evaluate this. This is a symmetrical shape. Our distance function is symmetrical. So we're just going to look at the we'll set this up for the first octant. So our moment of inertia about the z-axis, and I'm going to multiply by 4 because we're just talking about the first octant here, 4k. Theta is going to vary from 0 to pi over 2. Rho in the first octant, we're going from pi over 2 to pi over 4. So we're going from here to here. And then our radius is going from 0 to cosine phi. And our distance from the z-axis squared for our second moment of inertia, we get rho sine phi squared. And I think I put my shading in the wrong place. We're looking for the moment of inertia of the solid that's inside the cone. If we go from pi over 4 to pi, no, that's right, pi over 4 to pi over 2, so we're going from here to here. That was right. Rho sine phi squared, and then our dV is rho squared sine phi, d rho, d phi, d theta. So there's our integral. Again, not a tough integral to evaluate. So let's go through this evaluation. We get 4k, integral from 0 to pi over 2. the integral from pi over 4, pi over 2. Our first integral d rho. So we end up with a rho to the 4th. So we end up with, when we evaluate, we get rho to the 5th. Evaluated from 0 to cosine phi. So we end up with a cosine phi to the 5th. And we end up with a 1/5 here outside. And we get our rho to the 5th over 5. Cosine to the 5th phi, sine cubed phi, d phi, d theta. So this one we have to be a little careful with when we evaluate this. How are we going to evaluate the integral cosine to the 5th phi, sine to the 3rd phi? What do we want to do to that, d phi? Any ideas? So what I'm going to do for this integral, and this is a good technique to remember, is I'm going to write this as 4k over 5, the integral from 0 to pi over 2, the integral from pi over 4 to pi over 2. I'm going to factor out a sine squared from this sine cubed phi and leave one sine phi for my du, for my u substitution, and u is going to be cosine phi. So I end up with cosine to the 5th phi, 1 minus cosine squared phi, sine phi, d phi d theta. Oops, I did need a sine phi in there. Sine phi d phi d theta. There we go. And now I end up with, when I distribute this, I end up with a nice u substitution integral for cosine to the 5th and cosine to the 7th, and I have a du for my u substitution with cosine phi being my u here with my sine integral. So when I get this, I get 4k over 5, the integral from 0 to pi over 2 of minus cosine to the 6th phi over 6 plus cosine to the 8th phi over 8, and we're evaluating that on pi over 4 to pi over 2 d theta. And then from here on out it's not difficult to evaluate, because our limits on theta are from 0 to pi over 2, and we just end up with a multiple of pi over 2. So we just substitute our limits of integration in here, and we end up with a nice answer. So this technique, this trig technique for doing these trig integrals, that comes up occasionally when we're talking about spherical coordinates. That's a good one to remember. All right, questions? Okay. Homework. There we go.
Mr. Beaver?
Yes.
I actually do have one question.
Yes.